Well, hello. Today we're going to be discussing conjugate acid-base pairs. Just we need to understand what the word means and how to identify each of the conjugates. So let's get started. By definition, we know acids produce a proton. So here we have hydrochloric acid. It's going to donate a proton and something else will accept that proton. And what you'll be left with is the chloride ion. Now, whatever starts as an acid, after it donates its proton, what it becomes is called its conjugate base. It's really that simple. So we start with our acid, and we said, here we're looking at in solution, it's going to donate a proton, and then that proton will be accepted by another water to make the hydronium ion, and we'll be left with the chloride ion. That ion will then have a negative charge, and we'll call that its conjugate base, just to kind of repeat what I just said. All right, so let's look here. We've got hydrochloric acid in water, and it's going to produce the hydronium ion and the chloride ion. So again, whatever is donating the proton is identified as the acid. Whatever is accepting the proton, according to the Bronsted-Lowry definition, is a base. So in this case, water is going to act as a base. Now, we mentioned earlier that the HCl as an acid, whatever it becomes, is going to be called the conjugate base. And the water, if it's a base, after it accepts a proton, will now be acting as an acid. So this is one conjugate acid-base pair, the water and the hydronium, and the other conjugate acid pair is the hydrochloric acid and the chloride ion. You will always have one substance acting as a base, one acting as an acid in each case. Now the reason this is considered an acid is if we run this reaction in reverse, you can see that the hydronium ion will donate a proton and the chloride ion will accept that proton, and therefore the chloride ion will be acting as a Bronsted-Lowry base. It does not generally go from right to left, as hydrochloric acid is a strong acid. Generally, we use the term conjugates more for weak acids and weak bases, but I just want to identify it using the hydrochloric acid. So we could identify this as the hydrochloric acid is the acid, water is acting as its base, the hydronium ion is the conjugate acid of the water, and the chloride ion is the conjugate base of the acid. Let's do a few more for practice. Here we have ammonia in water forming the ammonium ion and hydroxide. So looking at this, let's figure out, is the ammonia donating a proton or accepting a proton? And you might ask, well, how will I know? Well, look at what it becomes on the product side. It goes from NH3 to NH4 1+. So clearly the NH3 has accepted a proton. Therefore, it's acting as a base. Where did it get that proton from? Well, it came from the water. The water started off as H2O, ends up as a hydroxide OH1-, so the water is donating a proton, hence it is acting as an acid. Now, to identify the conjugates, if the ammonia starts as a base, what it's going to end up with is going to be an acid, and because the water started off as an acid in this example, it ends up OH as its conjugate base. See, I could run this reaction in reverse, where the ammonium ion, the NH4 will donate a proton to the hydroxide to form ammonia and water. So this reaction can occur in both directions. The ammonia and the ammonium are conjugate acid-base pairs, and the water and the hydroxide are conjugate acid-base pairs. So looking at the bottom, I've identified ammonia as my base, and its conjugate acid would be the ammonium ion, and water in this example is acting as an acid, and it's going to be, its conjugate base is the hydroxide. So let's talk about water a little bit more. Water is special for many, many reasons. It hydrogen bonds and has a density where, as a solid, It is actually less dense than the liquid state. That makes water pretty unusual. It has an extremely high specific heat, which means it can hold a tremendous amount of heat before it turns to a gas. And it's also amphoteric or amphiprotic. What does that mean? Well, it means that that substance can act as either an acid or as a base. As an acid, it would donate a proton. As a base, it would accept a proton. Water is capable of doing both of these things, depending on which situation it finds itself in. In the first example that I'm showing at the bottom of this page, ammonia is acting as a base and accepting a proton from the water. So water's acting as an acid. In the top example here, I'm showing you water acting with hydrochloric acid. And now water is acting as a base, accepting a proton from the acid. And really, water is sort of a chameleon-like character. It will do whatever it needs to in the situation. When water is around a strong acid, it will act as a base. When water is around something that's very basic, it will act as an acid. And so this is what we mean when we say amphoteric or amphiprotic. I'm showing you just an example of that with molecules written out. This makes a little more sense to you. Here we have the hydronium ion, and here we have a hydrogen sulfate ion. So it's H, the little white dot, and then we have a big yellow S, and 1, 2, 3, 4 oxygens. This whole ion has a 1 negative charge. Now, if we look at this, the hydronium ends up becoming water. So that makes the hydronium the acid and the water its conjugate base. Now, if we look here, the hydrogen sulfate is accepting a proton from the hydronium, so it must be acting as a base, and the sulfuric acid is its conjugate acid. In the bottom example, I have the hydrogen sulfate ion, this time reacting with a hydroxide ion. And look at what happens. In this case, the hydrogen sulfate ion ends up donating its proton to the hydroxide to form the sulfate ion and water. So in this case, the hydroxide is acting as what? An acid or a base? Just think about it for a second. It's accepting a proton, so therefore it is acting as a base. And that makes the hydrogen sulfate acting as an acid because it's donating a proton. So the hydrogen sulfate on the bottom is acting as an acid, and the sulfate ion is its conjugate base. The hydroxide is a base, and what it becomes, the water, is its conjugate acid. So hydrogen sulfate ion is also amphoteric, can act as an acid or a base depending on what it's around. So we can look at this reaction occur. We have the hydronium ion. It's going to donate a proton. So there it goes. It donates a proton to the hydrogen sulfate ion. And what you're left with is the sulfuric acid and water. Now, generally in nature, the way these things work, sulfuric acid is a stronger acid than hydronium. So it will tend to go from strong, that is, in this case, from the right to the left would be the preferred way that Mother Nature wants to go. It would be extremely rare for the hydronium ion and the hydrogen sulfate ion to form sulfuric acid. It could happen, but it's not favorable in nature. Let's now look at the hydrogen sulfate ion in reactant, this time with the hydroxide. So in this case, the HSO4 is acting as an acid, so it's going to donate a proton to the hydroxide, and in this case, we're going to end up forming the HSO4 will become SO4 minus, the sulfate ion, and water. And again, this is the preferred manner for this reaction. Hydroxide is a stronger base than water, so things tend to go from strong to weak, and that's the way nature always wants to go. So let's summarize here what we've been talking about. Let's see if you can identify what's happening here. I need you to help me identify the conjugate acid-base pairs. So you might recognize this as acetic acid and water. Well, acetic acid is a stronger acid than water, so therefore what's going to happen is the water is going to act as a base when it's reacting with acetic acid, which means it will accept a proton. Notice that the water, it starts off as H2O, ends up as H3O+, so it accepted a proton. So therefore, the acetic acid is the acid, the water is acting as a base, and the acetic acid donated a proton, so what it became is going to be its conjugate base, and the water, because it accepted a proton, what it becomes is its conjugate acid. So if we were to link these guys together, the sulfuric acid and the acetate ion are conjugate acid-base pairs, and the water and the hydronium ion are acid-base pairs. I hope this is making some sense to you. So I've identified the acetic acid as my acid, and its conjugate base is the acetate ion. I've identified water as acting as a base in this example, and its conjugate acid is the hydronium ion. And as we mentioned, the reaction proceeds in direction so the stronger acid donates its proton to the stronger base. Okay, that's what's going to happen in each case. Finally, I'm going to end with this slide here. It's mentioning if something is a very strong acid, its conjugate base is very, very weak. Likewise, a very weak acid will have a very strong conjugate base. Hope all this makes sense. I hope you're staying healthy, and I look forward to us meeting very soon in person. Take care. Bye-bye.